Hello and most welcome to 1080 of the H series, and I will continue to investigate a little bit more in this most interesting connection between Heidegger and quantum phenomenology. Quantum phenomenology means that we carefully look into what is it to experience within quantum physics, or rather what doesn't have to come into the experience, because it's rather that the old way of seeing it, the everyday way of seeing it, it's putting limits on our experience and on ourselves. Something you can see in the book, The Matter with Things, are, although very common, everyday like, they are still very unhealthy, to blame for the explosion of mental/somatic diseases of today. These are things that gets questioned from quantum mechanics, of course, but it becomes even more clear once you take it down to a reasonable everyday level and you make a phenomenology out of it. Let me continue with François-Igor Pris and his lovely article. Although within quantum mechanics the notions of subject and object are meaningful, the ultimate quantum mechanical reality is that of the process of measurement, in which the subject interacts with the object, and in this interaction it is as though both become dissolved or inseparable from each other. Before the measurement, it makes sense to talk about a quantum system situated in a state. For example, in a state of superposition of eigenstates of a physical quantity, of a Hermitian operator, and also about the subject or observer which is independent of quantum system and does not interact with it. After the measurement, there is also an independent subject observer and a quantum system which is independent of the subject and which is situated in one of the eigenstates of the measured physical quantity. After the act of measurement, the physical quantity has a definite value. The result of its measurement is reproducible, but in the process of measurement, when the probabilistic reduction of the wave function takes place, it makes no sense to talk about the subject as such and the object as such. The process of measurement, reduction of wave function, or as Stefan Mango would put it, once you go from amplitudplanet and you enter into the frekvensplanet, everything changes and you got time and space that was not present previously. This cannot be called a physical process in the usual sense. It is unobservable and cannot be mathematized even in principle. The Born rules determining the probabilities of transition from a superposition state into one of eigenstates of a physical quantity, i.e. the probabilities of obtaining a definite result of measurement, only establishes a correspondence between the initial situation and the final situation. And does not say anything about the process of transition itself. The principal hypothesis of this paper, in favor of which some arguments are given below, is that it has a phenomenological nature in the sense of the Heideggerian Dasein. Quantum theory can be used as an instrument for preparing a given experimental situation. It seems that this demands more reflection on the foundations of the theory and the nature of reality than in the case of classical physics. But instrumentalism without phenomenology is not an appropriate philosophy of quantum physics. The result of application of quantum concepts, for example of the concepts of coordinates and momentum of a particle, is not predetermined. It is false or even meaningless to speak about the simultaneous existence of definite values of position and momentum. Of a particle, or about the existence of a well-defined trajectory of a quantum particle. Quantum concepts are rules, operators, for obtaining definite values. A definite value appears only as the result of an application of a quantum concept, that is, as the result of a measurement. For example, if the momentum of a free particle has a definite value, its position is absolutely underdetermined. In this case, the result of an application of the concept of a coordinate is absolutely undetermined. The coordinate with equal probability can take any value. A definite value appears only as the result of a process of measurement of the coordinate. Classical physical quantities represent some real numbers. This cannot be said about the corresponding quantum operators. For a given quantum state, they represent matrices, sets of possible values of physical quantities together with the corresponding probabilities. The actualization of a given definite value happens during the process of measurement. One can say that quantum concepts of physical quantities represent some quantum physical quantities, properties, which should be understood as dispositional ones. Suarez writes that the representation of a quantum property has no analogue in quantum mechanics. There is no analogue of this type of representation in classical mechanics. A quantum state is not to be interpreted a la classical mechanics as an assignment of actual possessed properties and their values, but rather as a mere assignment of probabilities. Although before the measurement of the position of the electron does not have any definite position, one cannot say that it does not have any position at all. The position of the electron, given its wave function, is a real dispositional property, which is described by the operator in its position. Now the quote from Suarez. That is why for Heisenberg, the atoms or the elementary particles form a world of potentialities or possibilities rather than one of things or facts. End of quote. In spite of its revolutionary character, the theory of relativity, special and general, is considered as a classical theory precisely because the concept used by the theory and the theory as a whole function in the classical regime. The observer measures the quantities whose concrete values exist before the measurement, though they depend on a reference frame, i.e. independently of whether or not the observer produces a measurement. The Einstein principle of relativity is saying that there is no privileged physical framework, that is, different observers observe different values of a physical quantity, does not take into consideration the relativity of the border between the observer and what is observed. In quantum mechanics, this border, in classical sense, is fixed only post factum, as the result of a process of measurement, or looking the game of Federer. A classical concept and the corresponding quantum concept can be understood as two aspects of one and the same more general concept. According to Mark Wilson, even simple concepts have a rich internal fine structure consisting of sub-concepts related to each other in different ways. Some concepts function as an atlas consisting of various partially overlapping leaves, maps. Here is one of his example, cited by Rodolph Random. Coming here. Mass, impressed gravitational force, and work required to move something relative to a local frame are some of the leaves of the atlas-structured empirical concept weight. In the case of the atlas structure here, there is a Wittgensteinian family resemblance between the different leaves of an atlas. A more complex conceptual structure is the patchwork one, proposed by Wilson. The various leaves in a patchwork are connected to each other at their edges. Such is, for example, the concept of hardness. Random describes this example as follows. Quote, hardness generically is something like resistance to penetration. To test such resistance, we might press a weight on a sample, squeeze it, strike it, scratch it, cut it, or rub it. The result of these various tests will not always be conciliant. End of quote. The generalized concepts of physical quantities representing classical as well as quantum properties can be understood as atlas patchwork ones. The domains of application of classical concept and the corresponding quantum concept are overlapped when the physical quantity has a definite value. His understanding of the relation between classical and quantum concepts is somewhat different from our own. The wave function and quantum reality. Let us illustrate the question about the quantum reality, quantum objectivity and quantum concepts by using the example of the wave function. It is known that the wave function suffers from the lack of objective reality in the following sense. A wave function can be determined in a statistical context when there is the possibility of performing measurements on its identical copies. If one deals with only one exemplar of quantum system situated in a pure state C, which is an eigenstate with the eigenvalue 1 of a projector, the function C is known only to the experimenter who prepared it, but cannot be known to an exterior observer. Indeed, if an observer performs a measurement, the system modifies its state irreversibly and randomly. A part of the information about the initial state of the system is lost. The experimenter obtains only partial information about it. As a consequence of this, it is impossible to copy exactly an unknown quantum state. This is called the no-cloning theorem. Hence, one should either accept the existence of unknowable reality, unknowable from the point of view of the observer, who is not implicated in the process of preparing the wave function, or recognize that the ultimate reality supposes the presence of the interactant subject observer. Independently of the observer, the quantum function cannot be considered as objectively real. The quantum reality is the reality of the act of preparing the state of the system. In the last case, the concept wave function cannot be viewed as a concept in the classical sense, but as a quantum concept, whose functioning supposes the presence of the observer. In substance, in quantum mechanics, concepts are functioning not as means for representing a metaphysical reality of objects, existing independently from the observer, but as rules for the interaction of the observer with the reality, for the formation of the classical metaphysical reality, which is secondary by the observer. Hence, the understanding of quantum mechanics should not consist of understanding quantum concepts in a classical way, which is not possible, but in an understanding that such understanding is not possible, that quantum concepts differ from the classical ones in the way they function. What has been said agrees with the following position, which Wilson attributes to Kant. The general claim is that our native conception of the objective concepts are as corresponding to real world attributes is incoherent. That every viable concept must inherently involve the constructive agencies of our own minds in some irrevocable way. End of quote. The measurement problem, the hard problem in the philosophy of mind, and the Wittgensteinian problem of rule following. The act of measurement, the action of the subject in the process of measurement, is being performed within an established scientific and ordinary practice, in accordance with implicit and explicit rules. That is why it's possible to dissolve the measurement problem pragmatically. Michel Bitbol, for example, proposed the Wittgensteinian dissolution of the measurement problem within the second philosophy of Wittgenstein. The dissolution consists of using the instruments and mathematical symbols in a way so that the problem no longer appears. This is not a naive avoidance of attempts to solve the problem. The Wittgensteinian dissolution of the problem is the initial point, but also the final point of a long series of failed attempts to solve the problem formally or discursively. Bitbol emphasizes that the quantum observation is not an observation of pre-existing entities. It is a practice organized according to the procedural rationalities guided by theoretical rules. The ontology in the sense of Quine is a secondary retranslation of this practice. The act of measurement is an execution of procedures which, for a certain class of well-defined experiential preparations, gives reproducible values. These values can be treated as secondary, as reflecting properties of objects. According to Bitbol, the function of I is to manifest an engagement in the double sense of this word. Engagement to accomplish something and engagement in a situation. The formalism of quantum mechanics taken in isolation from the practice of its application is incomplete, and a formal completion of quantum mechanics is impossible. Nevertheless, says Bitbol, a larger system including the quantum formalism, the probability rules of its application, and its effective confrontation with the achievements of every concrete experiential situation has been complete since the creation of quantum mechanics. Though at first sight no two philosophers are more different than Heidegger and Wittgenstein, there is no doubt that both are pragmatists. Brandom, for example, understands Heidegger's philosophy as a normative pragmatism. The normative social practice is primary, norms and rules are implicit in the practice. Phenomena, objects and the subject herself are secondary. They can be reconstructed pragmatically. One can agree with Rose that Brandom's anti-naturalistic interpretation of Heidegger should be turned on its head. Heidegger is a naturalist. Natural phenomena are primary. They contain in themselves their own implicit norms. It is pretty obvious that the second philosophy of Wittgenstein is also a specific normative naturalism. The Wittgensteinian language game governed by the implicit or explicit natural rules are both natural and spontaneous, normative. Moreover, there are some reasons to think that Heidegger's metaphysics is implicit in Wittgenstein's philosophy, and the Heideggerian notion of Dasein, literally being there, corresponds to the Wittgensteinian notions of language game and form of life. For example, the following characterization of Dasein is also applicable to the language games. Quote from Heidegger, chapter 2, paragraph 12. Dasein is an entity which in its very being comports itself understandingly towards that being. Dasein exists. Furthermore, Dasein is an entity which in each case I myself am. Minus belongs to any existent Dasein, and belongs to it as the condition which makes authenticity and inauthenticity possible. End of quote. According to Dreyfus, in contrast to Wittgenstein, Heidegger needs in a special technical philosophical language to theorize the background, i.e. practices. In other words, Heidegger's phenomenology makes explicit what is implicit in multiple Wittgensteinian examples. The philosophical literature indicates the existence of a close relationship between the notions of language game and form of life and Dasein. That is why Heidegger himself writes that language is not identical with the sum of total of all the words printed in a dictionary. Instead, language is as Dasein is. It exists. That is why one can suppose that together with the Wittgensteinian notion of language game, the Heideggerian notion of Dasein can be used for pragmatic phenomenological solutions of measurement problems in quantum mechanics. To be more precise, the notion of language game rather allows a therapeutic dissolution of the measurement problem. The notion of Dasein allows an explicit metaphysical solution of it. See below. The theoretical rules used by the subject observer for explanations and predictions are quantum mechanical phenomena and the real material quantum mechanical system. The things rules are being applied to are two complementary aspects of the functioning of quantum mechanics. During the process of measurement, one or another possibility is being actualized. The gap between the phase of theoretical prediction and the phase of asserting a result of measurement, that is, between the domain of possible and that of actual, is being closed pragmatically. Hence, the measurement problem can be understood as an instantiation of the Wittgensteinian problem of rule following, or as the problem of a gap between the quantum mechanical rules or concepts and their application, where the rule of quantum observer, thus of consciousness, is significant. This problem can be solved or dissolved a la Wittgenstein. The process of measurement is a Wittgensteinian process, a language game of the application of its quantum rules. The so-called explanatory gap problem in the philosophy of mind, which is also called the hard problem of consciousness, that is the problem of a physicalist or naturalist explanation of a phenomenal consciousness, can also be understood as a Wittgensteinian problem of a gap between a rule or a concept and its application. Hence, the measurement problem in quantum mechanics is an instantiation of the explanatory gap problem or the hard problem in the philosophy of mind. So, to conclude, we get two things for the price of one. Not only do we get quantum phenomenology, we get good old Wittgenstein back on the carpet, which I am really happy for, because once you know that Wittgenstein is in on it, you know it's healing going on. And I think quantum health that we started this series with was actually true. Quantum mechanics heals, and that's the only thing that can heal. These gaps, this lack of possibility of using concepts, and the confusion that inevitably ends in chaos, pain, disorder, mental disease. as so clearly proven by McGilchrist, the people suffering of mental disease, or the very majority of them, are getting all their stuff from ordinary uses of language. There's nothing odd with them. It's just the contrary. A schizophrenic is way too rational, or way too ordinary language user. Everything is a rule for him, but he doesn't understand the gap between the rule and its use. And therein lies the problem. And go further and further into the concepts will make the disease worse. And no wonder our educational system today fosters or creates sick people, because they do not look into the pre-understanding, the pre-established understanding, which is a complete disaster not to do that. It means that we're using tax money to make young children sick. And quantum health is going to save that, change that, to once more make us heal. So I'm looking forward to looking more into François-Igor Pris. I say thank you very much and have a very pleasant afternoon. Bye bye for now.